So people in the past have been using a variety of ways to do this. They have tried principal component analysis, additional learning, and deep learning more recently. And in our work, we find that a particular neural network structure called WaveNet can be used to more effectively remove noise in LIGO data. And this WaveNet was originally designed to generate human speech, but later it's also applied to speech denoising. So this is the general structure of the WaveNet. It might look complicated, but it's really just a series of matrix multiplication plus some nonlinear operations. So it takes a vector as the input, which is a time series, and ideally it should output a denoised version of this input time series. So we use a non-spinning binary black hole waveform to train our neural network, and the total mass ranges from 5 to 70, and the mass ratio is from 1 to 10. So the sample rate that we use here is about 8,192, and we consider 1 second long signal. So our input is actually a vector of size 192. So we first try our method on Gaussian noise. So this is the one scenario that we consider here. The red line here is the ground truth signal, and the blue line here is the mixed signal, which is the ground truth signal contaminated by Gaussian noise. And the input length is 1 second long. Okay, this is our result. So basically, as you can see, in this particular case, our neural network can reconstruct the ground truth signal pretty well. So after this, we also test our model on real LIGO detection. Oh, right. Well, yeah, so this is, to test the robustness of our model, we actually contaminated the same signal with different kind of Gaussian noise. And the upper panel is the contaminated signal, and the lower panel is the reconstruction of our algorithm. As you can see, our algorithm is quite robust against the variation in the Gaussian noise. And after this, we also test our neural network on real LIGO detection. And this is an example for the denoising of W150914. The upper left panel is the output of our algorithm, and we overlap it with the template of the same event. And the lower panel is the whitened version of our prediction and the same template. As you can see, at the range where the LIGO detector is most sensitive, our algorithm can reconstruct the signal pretty well. The overlap is more than 99%. This is another example. We consider another event which must lower SNR. So in this case, we can also reconstruct the original signal with more than 99% of overlap. This is another example. So we just consider a different event with different SNR. And like I mentioned earlier, we only trained our neural network on non-spinning black hole. So we're interested to see how would the neural network perform if we actually used it to denoise spin processing binary black hole signals. So in this case, we consider 3 types of template. So and we consider the same total mass, which is 70 solar mass here, and the mass ratio is 4/3. But we consider 3 different set of spins. And as you can see here, as we increase the magnitude of the spins, the performance of the algorithm actually deteriorates. But if we only restrain to small spins, our algorithm can still reconstruct the signal with an overlap of more than 99%. And after this, we try to test our same algorithm on the signal that is contaminated by a glitch. We consider 2 types of glitch. The first one is the Gaussian glitch. As you can see, basically, our reconstruction algorithm just ignores the anomaly in the signal. Right. So the upper panel is for Gaussian glitch, and the lower panel is for sine Gaussian glitch. Right. So basically, in both cases, our algorithm can ignore anomalies in the signal. So this is the last case that we consider here. We only consider glitches, so which means that we mix glitch with the LIGO noise, and we want to see how would the algorithm respond in this case. And as you can see here, if we only consider a small blip, then the algorithm will completely ignore that blip. And even we increase the magnitude of this blip, the output of the algorithm is almost the same. So which means that our algorithm will completely ignore this kind of a glitch. And things get more interesting when we consider sine Gaussian glitch. So on the lower left panel is our reconstruction and the ground truth glitch. So in this case, the glitch is a sine Gaussian glitch, and we also consider the whitened version of those two templates. So as you can see, if we look at the whitened version of the reconstruction, we can see that our algorithm can actually reconstruct the face pretty well. Right. So basically, to sum up, the application of deep learning to gravitational wave denoising is promising. So, we can actually get almost the same result with much fewer resources, and this whole process is actually much less time consuming. And the quality of the reconstruction is comparable to those done by human expert. And this whole algorithm can be easily integrated into the LIGO pipeline to accelerate the analysis process. Yeah. Thank you. Any questions?